All right, so you can expect, I'm sure you're looking forward to this with great joy. The Project 3 specification should come out today. I was expecting a reaction, something like that. And then let's see what else. Okay, so the Project 3 specification. I will also release, I think, a homework, although it will not be due for 2 weeks because you have another reminder, you have a test next week. Perhaps you may have, this may come as a surprise to you, but I hope not. So on Wednesday, in-class test, same format and so forth as last time. Okay, questions, issues. Silence. I'm impressed. Okay. Why do I get this sense that there's of a certain reserve, perhaps fatigue, amongst the people in this class? I don't know. It's strange. All right. So I did this, or I showed this. Particular implementation. We were in the middle of an implementation of going through another list of features, just as we did for functions, where you keep adding features of functions, and it causes the implementation to have to do various handsprings to keep up, and contortions. Here, we've been going through the same exercise, same sort of exercise, but with object orientation. So this time, the feature that just got added was inheritance. Was multiple inheritance, but but in this case, interface inheritance, as it is sometimes called in Java, which is inheritance of interfaces of signatures, but no bodies. That is to say, all the bodies come from the line of extended classes, and the interfaces simply give other classes or other methods a way of accessing, of processing more different kinds of objects. Sort of produces some cross connections between hierarchies of classes. All right, so, and the technique was to say, okay, well, the way that we get this to work, and the problem here was that you want to have a method here that can work regardless of what kind of C it gets passed. So that's statement one. Statement two is that that C can come from a variety of different hierarchies of classes, in this case A and B, and the problem is that class A2 and B2, according to the previous, if we're going to use the previous strategy for laying out for having classes work, classes A2 and B2 are constrained in their implementation to be like class A and B. And class A and B were constructed without any knowledge of C. I mean, they were just, I don't see a C, and there's no C in sight when you look at class A and B. So you have A2 and B2 are constrained by the decisions made for A and B. And so there is this problem, because that means that you have two distinctly arrived at decisions that both have to work when you get down here to C. And how can that happen? And the one solution is, well, you just have to be, if you lay out the virtual tables in such a way that the methods are all at the same location, then we can make it work. Then it works. Now, there's something about interfaces in Java. They are restricted in a particular way that makes this, not only don't they have bodies, but there's something else that you don't find in an interface that's kind of important for making this work. What is it? What else is not in a Java? What else can't you do, don't you do in a Java interface that you might conceivably do? I saw two hands. No, now I only see one hand. Yeah? Well, what else is there? What is there in a Java class that is not in a Java interface? Yeah. Pardon me? Instance variables. That's right. There are instance variables in Java interfaces, but it doesn't mean what you think. Those are all constants, and they are all they're used as it's a strange little feature that just got tacked onto interfaces to give them away before they had enumerals, to give them away to have enumerals before they had enumerals. That's right. Why would instance variables screw this up? Why would instance variables screw this up? Yeah, why would... Right, you don't know which choice of where, whoops, not this slide, let's see, the previous slide. You don't know whether you're facing a class that has A's choice of where the instance variables go, or B's choice of where the instance variables go. Oh, for that matter, yeah, right, so you don't know, presumably if I were allowed to have an instance variable, say, lowercase c, in interface C, then both A and B would have to have it, or at least A2 and B2 would have to have it, and somehow it would have to magically end up in the same place in both objects, and that gets a little difficult. Interestingly enough, there are languages in which you can do exactly that. You can have instance variables and have it work. So you can have different instance variables from two different things that you inherit from, and it will work. And that's as I recall, Eiffel has that property. And what you do is you simply say, well, rather than treat an instance variable as this funny thing that's a primitive, I am going to instead treat an instance variable as if it were a combination of a setter and getter method. Now in C++, one of the interesting features of C++ is that in fact you can define a method that returns a reference type as its variable, as its result. And that can, some of you have actually used this, I've noticed. It's a little dangerous if you aren't careful, but you can do it. So it can, you can return, for example, a reference to one of your members as a return result, which means that it gives you access to that member as if it were an ordinary variable. You can assign into it, you can fetch from it. And because it's a function, because these are methods returning these references, they can, of course, be overwritten, and you can, of course, and then you can get the effect, exactly the effect of having instance variables in your that you also can return if you feel like doing that. Or you can do another thing. You can actually make it as setter and getter methods. You can have the Eiffel language actually allows you to define what it means, and so does Python actually, to define what it means to fetch a field and to assign to a field. It's basically the field is sort of syntactic sugar for, dot A or whatever, dot X is syntactic sugar for a getter or setter method, depending on which way you're going. And this is interesting. It gives you, it sort of makes the interface that much more abstract. Okay, but so this is one solution to the problem, the brute force solution. Now, another solution is the one that was used, that is, I think, still used actually in Java implementations. And the idea is to make interfaces different. So, we will abandon the idea that a C is, from the implementation point of view, we will abandon the idea that a C is just a kind of A or B. Instead, we'll say that a C is a new kind of value, an interface value. And when you cast or when you convert an A or a B to a C, that's actually work. That you actually have to do something. It's all behind the curtain. You don't see any of it actually. The programmer doesn't see any of it except perhaps that there's a performance hit. So basically the idea is, do I have an illustration of this? Yes, here we are. So basically the idea is that I will represent interface values like this C here, lowercase c here. I will represent it as an actual object in its own right. And it's an interface type object. Now the compiler knows that it's accessing something whose static type is an interface, so there's no problem there. So basically, when I do this assignment, when I assign B to C right here, I will in fact create a new object like this, and this object will contain a pointer to the actual object B, and it will also contain a virtual table pointer that contains all of the necessary methods for C. So in this case, because this is a method formed from B, that means that this slot here, G, will contain the body 2, the B's body for G. So now, when I want to call the only thing I can do to a C, I can cast it to a B. That'll be easy enough. When you do a cast to a B, the thing will check that the types are okay, and then it will just return to you this pointer right here. That's easy. And the other thing I can do with it is I can call the G method. Well, to call the G method, I will simply find the body over here, and then I will pass this object as this parameter, and there you are. So I will, by the way, if that isn't clear to you, in Java, despite the syntax, foo.bar, there's nothing, despite what I call the worship of the first parameter, which seems to be the rule in Java and C++, there's nothing particularly magical about that first parameter. It's just a parameter that happens to be written to the left of the dot instead of after the parentheses. And this was apparently considered a good idea back in the 70s and has been carried on since. So to call the G method right here, we take the method, the pointer to the method body2 from this table, and we take this parameter from that object right there. So it's sort of as if we somehow magically interpolate c.obj .g at this point, but we accomplish it by this method. So I'm kind of surprised that they use this. This has the unfortunate property that using interfaces is expensive. You'd like it. I mean, if you're a sort of programmer, according to my heart, you'd prefer to keep your parameter lists as abstract as possible. You'd like to use interfaces all over the place, so that when you write a procedure that only uses the G method of all of these different types, that you can simply say, oh, well, then I'll pass it a C as its parameter, and everything will be fine. But this sort of this particular choice of implementation sort of discourages that. So one way of fixing that is to say, okay, well, this isn't exactly what we'll do it a little differently. And I don't think I have all right, this is wrong. I should definitely have an illustration for this. So the idea is that another idea is to say, okay, well, for every time that every class that I make, I'm just going to have the possibility that that class is going to have interfaces. I'm going to allow for the possibility that that class will be extended to have various interfaces, and so I will put an extra vector in that class that contains the information for each possible interface. So then what happens is that it makes calls still more complicated, but at least I don't have to create a new object each time, because what I do is I consult the interface vector of whatever object I actually have. I find in that interface vector somehow the thing that says, how do I behave if I'm to be treated as a C, and I pass the appropriate information from there. I think that rather than talk this through, this really should have had a slide for it. So I think I'm going to add a slide on describing this particular choice. But at least this increases the time cost also, but at least it decreases the overhead of creating a new object every time I have to use an interface. All right, so I will enhance this in the lecture notes for the sometime in the next couple of days, so that when you come to it, you can see what I'm talking about. Okay, so these are various ways of dealing with interfaces, and they work. They're very nice. But now let's just make things really difficult. This time in C++. And for that matter, in Python, you have this possibility of full multiple inheritance, in which you can inherit not only multiple classes, you can inherit classes that have instance variables as well. So this is an interesting problem, and it causes this really makes things particularly difficult for us. Now in Python, it's easy because in full Python, not our Python, but in full Python, it's easy because you just, everything is dictionary based. So, okay, so what's the problem? He asks for G, I look up G in my dictionary. What's the problem? And if I don't find it in my dictionary, well, then I look in each of my superclasses. Easy. You know, a nice recursive procedure, very simple, and never mind that it's as slow as molasses. It works and it's simple. That's the main thing. It's a very simple. It doesn't really complicate the implementation much at all. Okay, so here, but in C++, we aim to do something better. So here's the problem. I have these two classes, A and B, and I have a third class that extends both of them. I can't write this in Java, but I'll write it. But since I was using Java before, I'll continue to use it here. And the question is, in this class D, where exactly do I put X and Y? Now, I imagine that in this class G, I have an override for a method H that appears in both of these other two classes, A and B. Now, suppose that I have a D, some object of this type D, and I call the F method on it. Well, the F method is inherited from A. And if I assume that I'm going to reuse the body of code from F, if I'm just going to reuse the code from A.F, then that code is going to expect that the this parameter points to an A. So it's going to expect that it's got a pointer that's giving it the format of A, and that everything in it is formatted like an A, and everything is fine. Okay, fine. Likewise, AD.G expects that it points to a B, which is fine. And so that means that when G expects that the this pointer inside of it will have the format of a B, which means that the first variable in it will be Y, whereas F expects that the first instance variable in its parameter is going to be X. Well, now I have this method H, and H has some body here. That's fine. And that body is going to access, in general, you can expect that body to access X and Y. Okay? So where are they going to go? Well, that might seem obvious until you realize that for somebody calling just H, because D chooses some place to put the A part and the B part of itself, the X and the Y. So inside here, there's no particular problem in getting at X and Y. But wait a minute, up here, both G and F call H. And that means that G is going to call H, but it's this parameter that it has is going to be pointing to something that looks like a B. F is going to be calling H, but this parameter that it passes to H is going to look like an A. But the A part of a D and the B part of the D obviously have to be two different places, one before the other somewhere, which means that you can't have the same this parameter in both cases. How is this going to work? I mean, what one pointer can you pass from each of these that will allow that H can use to get at both X and Y? Well, something has to change here. Somehow somebody has to be aware of the fact that I'm not just an A. I'm an A that's inside a D. Unfortunately, I don't know what a D is. A is a completely separate type. It's never heard of D. Or B has got to know that it's a B, that this G is inside of D, or something like that. There has to be, or D has to know that I'm an H being called from an A, or I'm an H being called from a B. I'm an H being called assuming that this pointer is an A, and I'm an H being called assuming that this pointer is a B. This is somewhat of a quandary. So how do we solve this? So method one, I haven't looked to see recently how whether this still gets used, or to what extent. There are two methods that GCC knows how to use for C++. Here's a method that I believe was the first, and it goes like this. We're going to change the virtual tables. From now on, virtual tables will contain not just method pointers to the bodies of the various routines, but they will also, each slot will also be followed by an offset. Now, this offset will essentially tell you how much to adjust your pointer by before this pointer by before calling the method. So here's how it works. If you have an A, we have an A, a B, and a D. If you have an A, then its virtual table looks the same as always. You have virtual pointer to F, you have a pointer to H, And the two offset things are both 0, indicating that a this, an A, is a this that does not have to be adjusted before you call either of those methods. So you want to, a method call is just pick up the pointer to an A, look through its virtual table, find the method that you want, or extract the method that you want, F or G, and then add 0 to your this pointer, because there's a 0 in that slot, and call. Same for B, no problem. If I'm calling a B, then and I want to call either of those methods, no, I just do the same thing. Now suppose that I've laid out a D so that the they part is the A part is here, and the B part is here. So the way that I'll do that, my layout for a D will be that it'll be as if I have an A in front of a B, just an A concatenated with a B. I'll have both methods, both things, which means that I'll have two virtual tables. One for if I'm treating this as an A or as a D, and one for when I'm treating this as if it were a B. Now, if I have one of these, so if I have a D, and let's suppose now that I want to call, so D inherits from A and B, and it overrides H. Now, if I want to call the F method on a D, then I look at the table. I'll come over here. I'll see, okay, I call the body of, all I have to do is call this the body of A.F, and I don't have to adjust my pointer. Why? Well, because it just so happens that the beginning of a D looks exactly like the beginning of an A, so everything's fine. But if I call the B method, the G method on this D, well, then according to this pointer, the G method is down here. I will call the body of B.G, but just before I call it, I will increment or I will add 8 to this pointer, so that this will now be pointing right here. And D will get a pointer that looks like a B, and all of the operations that it does will operate on this part of the D. So far, so good. Now things get rather interesting. I'm now inside the body of A.F or of B.G. I'm inside the body. So I now have an object that looks like this, and I want to call the H method. Well, I want to call the G method. So I want to call the G method. So I say, okay, fine, I'll call G, and oh, look, because I've got a pointer that looks like a B, I don't have to adjust the pointer at all. I'll just call it, and everything will be fine. If, however, I call the H method, well, H expects to get something that looks like a D. In other words, it expects to get a pointer to this guy up here at the top of AD. I'm sorry, for the benefit of you on the screen audience, I have been remiss. I have been pointing at the wrong screen. So D expects to get a pointer to this thing right up here at the top. And but B is about to call, the body of B, of B dot say F or of G, for example, has this pointer right here, the pointer to this to the middle of the D object. How does it? And it doesn't know anything about D, so how does it know to adjust that pointer back to here? Well, no problem, because I actually have a modified virtual table for B, for this B part, that says when you call H, first adjust your this pointer by -8. and that will cancel the effect of this 8 over here. It will call the H method with the pointer right up here to the beginning of the D. Okay? That's an interesting implementation. Okay? So it means that now the big thing about this is that every single method call now has an additional addition that has to get done, an additional add that has to be done before the call. So this is a distributed overhead. Just because of the possibility that somebody might use multiple inheritance somewhere, every method call now has to be increased by some substantial fraction of the total cost of the method call, overhead to do that. So this is, as an implementation goes, it does the job in a confusing sort of way, but it's not simple, and it is kind of expensive in that regard. So this is just saying in prose exactly what I was just saying. So how do we fix this? Yes?
I just have a question. So in the last part, since H is in the class D,
Yeah.
both if you had triple inheritance or inheritance from 4 things, the parts for every single inherited method all have to be augmented. Body of H. Correct?
With a body of it, yes. Yeah, remember these virtual tables here, there are actually now 4 virtual tables. There is and these are different from each other. So so it depends on whether you are a B that is part of a D or a B that is a plain B and so forth. So I guess I don't quite see what you're getting at with augmented by H. What do you mean?
I can just ask it.
Okay. Yeah. Okay, so what's the alternative to this? The alternative to this is to say, look, let's not muck with the tables. Let us instead muck with the bodies a little bit. So I will, instead of having 2 different, of having these offsets, I'll have bodies of G, bodies of D.H and G.H. And the way this will work is that these bodies will be different. So this thing here define B.G to add 8 and then call B.G. What? No, that's not right. This should be D.G, sorry. So I use different body. I use a slightly modified body for G and for B's, for D's as opposed to B's. So the B that I call from inside D will always, so right here, let's see. So the G that I call inside D will first of all add 8 to this value and then call the regular G routine. So this slide looks wrong somehow. I'm going to have to look at this slide later today after I've gone through and made the necessary modifications. The idea here is that I introduce some new dummy procedures whose sole purpose is to increment the this pointer and then call the real method. Now that means that as long as I'm using normal inheritance and I don't do any of this double inheritance stuff, I will never have these, I will not use these dummy methods. There will be no overhead, no additional overhead caused by multiple inheritance. as soon as I introduce multiple inheritance and use it from within and use it from within something that uses multiple inheritance, then I will have to start introducing these additional bodies that do some extra computation. However, don't trust this slide quite yet until I've gone back and reviewed it, because this appears not to quite say that. All right, so with this trick, multiple inheritance now, now you can use it without guilt, because it now works without incurring any additional overhead in the case that you aren't using it, and that's a good feature. Now, there's still one feature of C++ that I haven't talked about, because it's getting a little out there, and that is the virtual base classes. So one of the unfortunate complications of multiple inheritance is that if you inherit from two classes, both of which inherit from a common class, so you get one of those diamond things. I have A, B and C inherit from A, and then D inherits from A and B. The poor little class down there at the bottom no longer knows, okay, well, you have one inherited method that came from B to D from A up here at the top, through B and through C. So which one of them do I use? Well, they're the same. Well, I don't know. I'm not sure about that. Which one of them do I use? How do I do this? And it's a strange confusion that was introduced by C++, and it takes some real work to fix that. And I didn't find it terribly interesting, so I'm not going to. I didn't find that I used those sufficiently often to justify going into it here, so I won't go into it here. But it is one more problem that we haven't handled. All right, so this gives you some idea of how multiple inheritance is held, and how inheritance in general is handled in a statically typed language like C++, in such a way as to make it as fast as possible. So you have the possibility of a completely dynamic implementation, as in Python. And that's flexible, it's simple, and the problem is only that it might be kind of slow compared to what it could in principle be. So in Java and C++, at the cost of some complexity, you can get inheritance at relatively low cost, and it's all good. Okay, so but this is how it's done, and I hope this gives you some idea of the kind of complications that fairly simple language decisions can cause. All right, questions on this? If not, I don't know. We'll have a little bit of time to start talking about the next subject, or I can talk about other things. We'll see. But let's take a brief breather and then see if there's anything else to discuss before we leave.
We go back a couple slides.
Mm-hmm.
Okay, so I guess my question is...
Where?
Oh, one more back. Yeah, here.
Mm-hmm.
So since H is redefined by class D to... Well, I guess, so say there was a method like X. That's a bad choice.
Let's call it a method like E, all right?
Okay. So say there was a method E that was defined newly in D. Would it have to go in both the A part of D's virtual table and the B part of D's virtual table?
No, it would only have to go into the first part.
It would only have to go in A's part?
Yeah, because you see the top virtual table serves as both a virtual table for A and a virtual table for D.
Okay.
So it's an A-like virtual table and a D-like virtual table. So the first part, this table behaves just like ordinary single inheritance.
Okay.
Right. So that the first class, just like ordinary single inheritance, except that you still need these offsets here. It's this table that's a little bit different.
So all you do is you take the first table and you augment it with any additional procedures that D has.
Right. In fact, I could probably. You're right. I could. No. B has an H. Yes. Okay. Fine.
Okay.
So it does not need an F pointer.
But if there was an E method, it would only be found at the bottom.
Yes.
Okay.
That's right.
All right. Thank you.
Right.
Professor,
Mm-hmm.
a quick question about in class D.
Mm-hmm.
There's one explicitly called A.H. If one wants to reuse the code in.
You mean when you say A.H, you mean as in A::H in C++?
Yes.
That is an interesting problem. Wait a minute. So the question is it going to do it right? Let's see. So.
I guess this question extends not just to the single.
Yeah, well, it should. No, I mean that should work just fine. You call. You pass. Yes, you pass the D pointer. You pass your pointer, the AD pointer, to A.H, and yeah, that would work. Yeah.
How do you link to the method, or how do you point to the A.H method from within? From within the body of the D.H method.
What do you mean? How do you point to it? I mean, you can. We call it just A::H, if that's what you mean. As for pointing to it, I mean, remember that from the point of view of the linker, which doesn't understand all this fancy object-oriented stuff, it's just a function body. It's just some function body. It has some weird mangled name. I don't care. I mean, you tell me that I'm supposed to call the foobar procedure, I call the foobar procedure. I won't tell you that you have violated object-oriented structure because I don't have any idea what that is. All I know is that there are bodies of code and I have pointers to them. Yeah, that's it. Yeah. Okay, let's wrap up here a bit. So the next topic will be we'll start getting into code generation just in time for Project 3. And we're going to be doing, this semester, we're going to be generating code for the IA32 architecture. This is the Intel, I think most people probably call it 8086 or something like that, or one of the other names, but IA32 is the name of the family of 32-bit architectures that is familiar to anyone who's used a PC. Now, we have some materials on this. There's a tutorial material in that's linked to off the web page by Robert Dewar at NYU. And there is also, for the intrepid who are curious, a link to some old Intel documentation on the IA32. It doesn't contain all the latest instructions, but it does contain a fair amount. It certainly contains everything that we're going to be using. Now, I apologize that there is this problem with, for some reason, inventors of hardware believe that they have to come up with a completely new assembly language every time they come up with a new architecture. And I don't mean just new, obviously they have to have new opcodes, but they also seem to think you need new syntax. And so there are n different kinds of syntax for all these different, every assembler I've ever seen, even though they're really all the same, they all have different syntax. And it's completely gratuitous, and it's caused by giving some intern the job of coming up with the assembly language every time. And I don't know what it is. It's some strange thing. Nothing against interns, but the fact is that they don't know very much about other assembly languages, and so they think they have to do things from scratch. And they get creative. There are certain times when it's not good to get creative, and inventing assembly languages is one of them. But the result of this is that there are two different assembly language formats for the IA32. There's the Intel format, and then there's the GAS format, GNU assembler format. And I'm afraid that occasionally, I will try not to, but occasionally we slip back and forth. So the tutorial notes from Dewar et al. Are the Intel format. And you can persuade GCC to produce that. You'll see in the Project 3 spec how to do it, but there's a parameter that allows you to cause GCC to do that. And probably it will cause less confusion, I suspect, if we use that format. So anyway, these are things that you can, when you aren't studying for the test, for the upcoming test, these are things that you can perhaps cast your eye over because we are going to be using them now. And I think I will not get started on that subject since we are out of time. Okay, further questions? If not, let's see you. Have a nice weekend.